As an example of the sort of situations we can model with linear differential equations, let's look at population growth. So let's suppose that we have a population of insects that without predation grows from 1,000 individuals to 1,100 individuals in 10 days. So let's model this population. So we'll find population function p of t. So one important thing about this sort of unconstrained population growth scenario is that typically the growth rate of a population is proportional to the size of the population. So if we translate that into mathematical language, we get, right, the growth rate of the population, that's dp dt, and the size of the population is just p. So remember, proportional to means it's a constant times. So we have some constant times p. Okay, so even just translating this first sentence, you see we get a differential equation. And so we could stop and solve this differential equation right away. We don't know this constant of proportionality yet, but we have some other data here, right? We know at time 0, the population is 1,000, and we know after 10 days, the population is 1,100. So since we have these 2 extra data points, this should be enough information to find 2 unknown constants. One of them is going to be the constant of integration that we get when we solve this differential equation, but the other hopefully will be this k. So we should be able to solve for k. All right, so let's go ahead and solve this. Now this differential equation, it is linear, but it's easier to solve it as a separable equation. So to solve it as a separable equation, let's multiply both sides by dt, divide both sides by p. This gives us dp over p equals k dt. So then we're going to integrate. We get natural log of p is k times t plus a constant. Now exponentiate. We get p is e to the kt times e to the c, and as usual, I'm going to rename e to the c a, so a e to the kt. So now we know a general formula for our population function. It looks like exponential growth. We just need to use our data points to find the unknown constants capital A and k. So let's use our initial time 0 point. So we know that that's 1,000. But using our formula, when we plug in t equals 0, we get a times e to the k times 0. And that's just a. So now we know a. A is 1,000. Okay. Using our other data point, we know that p of 10 is 1,100. We know a is 1,000. And then plugging in t equals 10, we get e times e to the k times 10. Okay, now this is an equation where k is the only unknown, so we can solve for k. So divide both sides by 1,000. 1.1 is e to the 10k. And then looks like we're going to need a natural log here. So taking natural logs on both sides, I get 10k is equal to natural log of 1.1. So 0.09531. And so k is 1/10 of that, which is 0.009531. And now we know our population function. It's 1,000 times e to the 0.009,531 times t. Okay, nice, not too bad. Of course, this was all without predation. So let's ask ourselves, how could we modify this model to account for predation? So let's suppose that there's a population of birds in the area that eat 50 insects per day. Without predation, we have 0.0, dPdt is 0.00953 times p, but then we need to subtract off the rate at which insects are being, right? This first term is the rate of new individuals. It's the rate at which new individuals are showing up in the population. So what we need to do is then subtract the rate of predation, the rate individuals are being removed from the population. And the rate of predation is 50 insects per day, so we can just write 50 here. All right, now this differential equation, it's still linear, but it's no longer separable. So, well, it is separable, but I want to solve it as a differential equation, just as an exercise, I guess. So let's rearrange it to make it look like we expect for a linear differential equation. So dp dt minus 0.009531 p equals negative 50. Okay, we can find our integrating factor. It turns out it's e to the minus 0.009531 times t. So multiplying the equation by that, just to save a little time, I'm going to name this constant minus k. And then at the end, we can write it out again. I just am getting tired of writing out all these decimals. So multiplying everything by mu, we get e to the minus kt dp dt minus k e to the minus kt times p equals e to the minus kt times minus 50. Okay, now this left-hand side ought to be the derivative with respect to time of e to the minus kt times p. And you can check that it is. Oops. On the right-hand side, minus 50 times e to the minus kt. Okay, now we can integrate on both sides. On the left-hand side, we get e to the minus kt times p. On the right-hand side, we get, let's see, 50 over k times e to the minus kt plus a constant. And then finish solving for p. So p is 50 over k plus c times e to the minus kt. Okay. So you can see, remember k is what? K is 0.009531. So we can put all of that into this now. So 50 divided by 0.009531 is 5,246 plus some constant determined by an initial condition times e to the minus, this shouldn't be a minus, this should be a plus, right? When we multiply everything by e to the kt, this is a plus. So plus k, which is 0.009531. So there's our population function.